Greetings. My name is Promit Chakroborty, and I'm a third-year PhD student at the Johns Hopkins University. This presentation is my submission for the Student Recognition Award at ICASP 2023 and is titled Efficient Reliability Analysis Using Generalized Multifidelity Modeling and Explainable Active Learning. This work was done in collaboration with the Idaho National Laboratory, and I would like to thank my co-authors, Professor Michael Shields and Dr. Som Dolipala. As civil engineers, we are all aware that systems fail and that when they do, they can cause massive damage to property and loss of life. Thus, it is our responsibility to understand why systems fail and how they fail. One of the ways in which we can understand system failure is by the failure probability of the system. To quantify this, we use a tool called reliability analysis. However, there are some challenges associated with reliability analysis, especially for complex real-world systems. For one, the input distribution of the system might be complicated, thus making sampling from it challenging. Secondly, it might be difficult to reduce the variance associated with the failure probability estimate. That is, it might be difficult to give a confident estimate of the failure probability. And finally, often for complex real-world systems, evaluating the system response at each sample point is prohibitively expensive, perhaps taking off the order of hours or even days to compute. The work we show here aims to tackle this challenge and reduce the response computation costs for these cases. How do we do so? The general method to do this is by using surrogate models, which are basically just approximate representations of the system response. There are broadly two ways to build surrogate models. The first is multi-fidelity modeling. Here, we first understand that we have something called high-fidelity models, which are basically the most complete and accurate representations of the system response available. However, because they are accurate and complete, they are often highly expensive. In multi-fidelity modeling, we use instead what are called low-fidelity models that are comparatively cheaper than the high-fidelity models because they incorporate some approximations or idealizations or reduction in dimensionality, etc., which makes them cheaper but also less accurate. However, these low-fidelity models at least have some sort of foundation in physics. On the other hand, we can use machine learning where we use data-driven approaches to learn the shape of the response function and thus predict the response at new points that we have not observed yet. Machine learned surrogates are extremely fast and extremely accurate, but they often lose the foundation in physics. However, we can leverage both methods and therefore create a procedure that considers both the physics at play and retains the predictive accuracy. This is our contribution. We basically propose a surrogate modeling framework and fit it within a larger reliability analysis algorithm, which has three major pieces. The first is the sampling and failure estimation. Secondly, we have the surrogate formulation itself. And finally, we have what is called the sufficiency check and active learning. For the first piece, for sampling, we use the subset simulation algorithm with any robust Markov chain Monte Carlo sampling algorithm. For those who are unaware, the subset simulation algorithm is the current benchmark for rare event reliability analysis and progresses as the schematic shows on the right of this slide. Basically, we take the input domain of the system and divide it into a sequence of subsets that converge to the failure domain. Next, we sample from each of the subsets in turn and estimate the conditional probability that a sample lying in subset I also lies in subset I plus 1. Then, using the laws of conditional probabilities, we can multiply all of these conditional probabilities together and get the target failure probability that we desire, as shown in the equation on the bottom right. The second piece is the surrogate formulation. Here, we first assume a couple of things. The first is that the high-fidelity model is the true response, basically the best we can do in terms of calculating the system response. We call the high-fidelity model and denote it as the function h. Secondly, we say that we have n number of low-fidelity models, each one denoted by L sub I, where I goes from 1 to n. The first step in building the surrogate is to train a machine-learned correction term. And for this, we use the Gaussian process regression algorithm, which I will talk about soon. But we train a machine learning correction term to estimate the discrepancy between the high fidelity model and each of the low fidelity models. Thus, we have n number of GP correction terms, where G sub I is basically equal to H minus L sub I. After this, we build what are called the corrected low fidelity models, denoted S sub I, which is where the ith corrected low fidelity model is basically the sum of the ith low fidelity model and the ith correction term. You will notice that each corrected low fidelity model is in itself an approximation of the high fidelity model. Once we have all the corrected low fidelity models, we assign probabilities to each of them, and these probabilities are local, that is, they depend on the sample point X. And once we have the probabilities and the corrected low fidelity models, we assemble them together into the final surrogate called S. However, before I talk about the assembly or the probability assignment, a quick overview on Gaussian process regression, which is the machine learning algorithm we use here. In this algorithm, we basically approximate the response function as the specific instance of a Gaussian process, where the data is used to train what is the best fit Gaussian process for the given function. Under this assumption, at any new point, we basically get a distribution of possible responses, and this distribution is Gaussian. By convention, we use the mean of the distribution as the estimate of the response, and we use the standard deviation of the distribution to estimate the error in the response that we predict. Okay, to talk about the assembly strategies, there are broadly two ways of assembling the corrected low fidelity models to build the final surrogate. The first is called model averaging, which is basically a weighted sum of all the corrected low fidelity models with the probabilities acting as the weights, as you see in the equation on the left. The other broad scheme is called model selection, where we basically at each point choose one of the corrected low fidelity models to serve as the surrogate for that point. There are, again, two ways to do model selection. The first is called deterministic selection, where basically at each point X, we choose that corrected low fidelity model, which has the highest probability assigned to it, as denoted mathematically on the left. On the other hand, we can also do stochastic selection, where we say that, okay, we have at any point, we have a bag with all of the corrected low fidelity models with probabilities assigned to them. And for that point, we pick one of the corrected low fidelity models at random in accordance with the probabilities assigned. Thus, if we have two models where model 1 has probability 0.8 and model 2 has probability 0.2, then we pick model 1 at that point 80% of the time and model 2 only 20% of the time. Okay, to do the assembly, we need to first assign model probabilities. How do we do this? We do this based on the hypothesis for what is the best model. In our algorithm, our hypothesis is that the best model is that which has the greatest probability of having the smallest correction magnitude. We can extend this to therefore say that the probability assigned to model K is the probability that model K is the best model, which is the probability that model K has the smallest correction magnitude, which is a measure of belief in model K. And this is denoted mathematically in the third and fourth points. Once we recognize that the correction magnitude is basically the absolute value of the GP correction term, we can use some laws of probability to compute to derive an expression for the probability assigned to each model in terms of this integral as shown in point 2, where small f is the probability density function of the kth correction magnitude, and capital F is the cumulative distribution function of the ith correction magnitude, where you notice that each of the correction terms are GPs or Gaussian distributions. However, you will recognize that here there is no talk about the cost of evaluating each of the low fidelity models. Here we assume that all the costs are the same, and we only look at the predictive accuracy of the different models. However, with a small change, we can incorporate the cost. And to do that, we just modify our hypothesis a little to say that the best model is that which has the greatest probability of having the smallest cost biased correction magnitude, where the cost biased correction magnitude is just the multiplication of the correction magnitude, which is absolute value of G, times this gamma function, which we call the cost biasing function. This function that we propose a certain build of this function, which is tau raised to the beta, where tau is the computational complexity or perhaps the time taken in each evaluation of the model, and beta is a tuning parameter that we can use to control the biasing level. Once we compute the cost bias correction magnitude for each of the models at a point, we can use the same equations as before to compute the probabilities for each of the models. Finally, our third piece is the sufficiency check and active learning. The basic idea here is that we want to ensure that at each point, the surrogate has some baseline level of accuracy. And to do this, we compute what is called the U function at each point. The U function gives us a guideline to understand whether or not surrogate prediction is sufficient or not. And if the surrogate prediction is seen as sufficient based on the U value, then we use the surrogate estimate as the response estimate for that point. However, if the U function says that the surrogate is not sufficient at the point, then we call the high fidelity model and use h of x as the response at that point. And then we use this extra data to retrain as many of the Gaussian process correction terms as we need, which helps us to refine the surrogate for future use. The U function was introduced as part of the AKMCS algorithm by Ashard, Gayton, and Lemaire, and has the following form, where S is the well-known surrogate prediction, the surrogate that we have defined, sigma is the standard deviation of that prediction, and F sub S is a subset-dependent failure threshold as chosen by the subset simulation algorithm itself. To compute the standard deviation of the prediction, you can notice that for the selection strategies, the surrogate S is basically a single Gaussian distribution, whereas for this averaging case, S is basically the weighted sum of Gaussians, and therefore it's still a Gaussian, so we can easily compute sigma G. Now, the U function allows for a probability interpretation, which leads to the sufficiency criterion, which states that if our U value is greater than a pre-specified threshold, then we say that the surrogate is sufficient at that point. Otherwise, we say that the surrogate is insufficient. Finally, some quick results. Here we consider an analytical rigid plastic portal frame example, which has 4 moment capacities at the 4 points, 1 through 4, and has 2 applied loads given as the P's, and it has 4 collapse modes. The equations associated are given on the right side of this slide, where L1 to L4 are each of the individual collapse modes and are also the low fidelity models considered for this example. The high fidelity model and the true response, therefore, is basically any one of the collapse modes occurring as shown here. And our input vector is basically all of the M's, M1 through M4, and the 2 applied loads, PH and PV. We consider 2 cases of this example. One is the 6-dimensional case, where all of the M's and all of the P's are taken as stochastic with distributions as shown in the middle column of the table on the left. And we also consider a 2-dimensional case where all the moment capacities are constant, but the applied loads are stochastic, as shown in the far right column of the table. Here we present the results. On the left, we see the table that compares all 3 of the assembly strategies of the proposed method to subset simulation for the 6-dimensional case, whereas on the right, we compare the 2-dimensional deterministic selection assembly strategy to both crude Monte Carlo, called CMC, and also subset simulation. The first sort of collection of rows in each of these tables shows us that the proposed algorithm estimates the failure probability very accurately as compared to subset simulation, and also with the same level of coefficient of variation as subset simulation provides. And the final collection of rows shows us in terms of the R-square value that the surrogates built by the proposed method are very accurate, since the R-square values is very close to 1. However, I draw your attention to the middle collection of rows, which shows us that where subset simulation and crude Monte Carlo require the high fidelity model to be evaluated at each of the generated sample points, our proposed method only requires the high fidelity model to be called at a fraction of the sample points, which is more clearly shown in terms of the percentage of total samples where the high fidelity model needed to be called. You will remember that the high fidelity model is assumed to be much more expensive than the low fidelity model, and this is the case in most real-world examples. And therefore, this reduction in high fidelity model calls represents a massive savings in the overall computational time. Finally, a quick figure for the 2D case, where we compare the failure surface of our proposed method, which is the dashed orange line, to the exact failure surface of the problem, which is the solid blue line. And we see that the predicted failure surface matches really well with the exact case. Finally, some closing comments. Our surrogate formulation significantly reduces computational expense by reducing the total number of high fidelity model calls required. But it still maintains the foundation in physics, which is not very common amongst machine learning frameworks. Secondly, when a system is known to fail in one of several modes, our algorithm, when run in a selection scheme, can be used to learn the dominant mode of failure in any region of the input or parameter space. Due to a lack of time, I could not discuss this in this presentation, but there are more details in the paper. that I submitted to the conference. And finally, we have a general framework here that can be used with various algorithms as required by any specific case, making this a versatile solution. Finally, a quick word on limitations. Since we use Gaussian processes, we have all the limitations of Gaussian processes, which is that our algorithm only works for smooth functions, and there is, at extremely high dimensions, our algorithm breaks down because Gaussian process breaks down in both of these cases. Secondly, our algorithm is not the cheapest possible since we use still physics-based low fidelity models, but it still saves a lot of computation time overall. Here are some quick references. Thank you.